Are there any questions on the material from chapter 6 before we start moving on to chapter 7? No? Okay. So if not, then let me start with chapter 7. Chapter 7 is what's called transverse shear. It's related to beam bending. It actually comes about from beam bending. So if you remember when we talked about beam bending, and I had the little picture cut out of the book where we assumed all the planes, when they bend, they stay planar and they remain perpendicular to the cross section, right? That was the beam bending assumption. In this chapter, we're going to talk about shear, transverse shear, and how that's needs a little bit of a small correction onto beam theory. We're still going to use a lot of the beam theory, but a slight correction onto it. So, like, just as a motivation, here, this is a book, right? You know, paperback book. You can pick whatever you want, right? But I drew on the edge some markings, right? And so those are cross. Imagine this is now a beam, right? So we have the cross sections, and then I also have drawn what would be sort of like the neutral axis, right? Now, if I bend this, you can see obviously that those cross sections do not stay perpendicular to the neutral axis, right? They actually kind of almost stay vertical, right? Which is definitely different than what we talked about for our beam bending assumption in chapter 6. The reason is that the pages are not glued together, right? There's, you know, if you have a regular beam, like if you try, I won't try to do it, if you try to bend like your phone, right? It has much greater resistance because the material is integral or bonded across those. In here, the pages are not fixed, and so when you bend it, they can freely slip relative to each other, or they don't resist any shearing between the pages, okay? So the book has no ability to resist the shear. That shear is what we call transverse shear, okay? So in the book, again, you can see it deform because there is actually no resistance to that transverse shear, okay? All right, that's what we're going to see. And actually, materials have that. Beams do have that. You know, the book is the extreme case of that where there's actually no ability for the material to resist that shearing, okay? And that's what we're going to talk about in this case. So still, for most beams, the stresses in general due to bending, the MCNI, are the dominant ones. But there are situations, especially if you have beams that are higher and stubbier, like, you know, stubbyish beams as opposed to long, slender beams, where the shear stresses can become significant, okay? All right, so let's talk a little bit about that. So I got a couple of slides, and I'll try to derive the equations as quickly as possible. This one, it's pretty straightforward. There's just really two equations in this chapter, but you have to be careful about some of the definitional type of stuff. So, okay, so fine. This is out of the book. So the book has pieces of wood that are not bonded together, right? And so here you can see each one of these pieces of wood would kind of go like that. Whereas when you bond them together, right, they actually would stay perpendicular, okay? And that's what we're talking about. The shear stress that happens between these layers. All right, so how can we calculate that? So what we've got here is, this is a cross section of a beam. It's a little, you know, differential length here, dx, okay? And now we have a neutral axis, right? And we want to look at the shear that happens at a plane, a distance y prime, there should be a prime there, y prime from the neutral axis, okay? So we kind of look at the side view in this figure, all right? And that's what's going on here. So if you look at this, right, we have,
Professor, you're not sharing your screen.
you sure? It says I'm sharing.
Yes, he's sharing it.
Oh, okay. I'm sorry. I can't see it on mine.
Is it good? You can't see it on your end? Some people can't see it? That's weird. Okay. All right. But most people can see it, I think, right? Okay. All right. So fine. So here we're at the position X, and we have an internal bending moment M. And then if we move down a little bit farther, a delta X or dx, they're using the finite differential in this figure, the bending moment might change by some amount dm, all right? And here you can see the stress distribution due to that bending moment. So what's going to happen is you can see the max stress here on the right side is a little bit bigger than the max stress on the left. Because the moment has changed, right? Because the moment has changed. So basically, if we were to look at, so we know that the stress, the bending stress is my over I, right? And if we were to look at the net force due to the bending stress on the left side, okay? So I'm going to call this F due to bending, right? The F due to bending, we would get just by integrating the bending stress, the sigma over that area. And that area is going to go, it's this area here. So we're going from y prime to the outer distance C. So we're just integrating over this face. And that would be the integral from y prime to C of my over I, and then over that area, okay? Now, on the left side, we're gonna have a different force because the moment has changed a little bit. So this is gonna be an FB plus a little change. So on the right-hand side, the FB is gonna be, well, I should do it this way, sorry. Is going to be the same thing. It's the integral from y prime to sigma, but this is going to be the stress plus the little change in stress. Or if we put it into this, if we put the bending moment in here, it's going to be the bending moment plus the little change. So we're going to get integral from y prime to c of y over I, the bending moment plus how much it changes because we've moved dx, all right? And then clearly you can see from this that the delta FB is due to this delta M, right? So delta FB is gonna be just that y prime to C of y over I M T A, okay? All right. Okay. All right. Now, so that means that there's a net force acting on this body that wants to move it, you know, assuming the moment increases if we go to the right, that this delta F, this change in force due to the change in the bending moment wants to push this element here to the left. So obviously that has to be kept in equilibrium. So what resists that is a shear force down here on the bottom, okay? So if we were to redraw this, what we have is this little element like this, all right? And again, this is at a distance y prime off of the neutral axis. This distance here is delta x and we have a force acting on this direction and this direction due to the bending. This is the force due to the bending, and this is the force due to the bending plus the change. And then to resist that, we're going to have a shear force acting this way. So this shear force has to equal delta FB, right? To keep it in equilibrium. And we know that the shear stress on that surface would be the shear force divided by the area at axon. So the area at axon is going to be this area here, right? So that is delta X times the thickness of the cross section at that plane Y prime. It's the thickness exactly at Y prime. So I'm going to call that T. All right. We know that V has to equal delta FB. So this now becomes the following, right? All right. I and delta M, they don't change with Y. They're constant over the cross-sectional area. So I can take those out. So I have delta M over delta X times T times I times this integral from Y prime to C of Y dA. And now if delta X goes to 0, what we have here is the derivative of the moment with respect to X. And if you remember from when we did the graphical solution for the moment diagrams, dm dx is equal to the shear, right? That's the shear from the shear diagram, V, all right? So now what do we got? We got tau, the shear stress is V over I times T times this integral from Y prime to C of Y dA. So, that's, again, we're integrating over this surface here, this face here, just on not the full area, but from Y prime up to the very top. So this, again, is another geometry integral. We call this Q. We give it the letter Q. That is the first area moment for the area above the plane where we want to find the shear, okay? We'll talk about what that means in a second. I probably need more space, but whatever. So this now, do I have another slide? Okay, so that tells me now that I have the shear stress equals the shear from the shear diagram, V, times this integral Q, which we'll talk about in a second, over I. That's the I of the entire cross section because it came from my flexure formula relating the stress to the bending moment. And then finally, the last one is T, and that's the thickness of the cross section at the plane where we want to find the shear stress, okay? And this is going to be our shear formula. So let me rewrite it here, and let's just define it, right? So the shear stress, and this is, look, I'm going to write it bigger, it's VQ over IT. So depending upon what plane, we want to find the shear stress, this distance Y prime, right? You could find this at any distance. If you go back to the book, you might want to find the shear stress at between 2 pages or between another set of pages, right? That plane, we have to talk about what plane we want to find the shear stress. So the plane is defined by Y prime. That tells us the plane of interest. All right. So this is the shear stress on the plane that's Y prime from the neutral axis, right? You want to find the shear stress on a different plane, you have a different y prime. Now, that's going to equal V, which is the shear from the shear diagram. Right? Now, that's constant over the cross section. Divided by I. This is the I for the cross section. This is the same I from the flexure formula. All right, it's the same one we used to compute the bending stress. Now this thickness, this is the thickness at the plane. Right, so it's this thickness right here. It's the plane of interest. Here is that thickness T. Okay, it has to be at the plane. The thickness at the plane, we want to find that shear stress. And then finally, we have Q, which is the goofy integral. And that's going to be the integral from y prime, starting from here up to the top. So we're integrating over this whole area here. All right, of y times dA. Okay, that's how we calculate the shear. Now, we know, like, doing integrals, avoid doing integrals. Most people find this preferred. And fortunately, this integral we can deal with a little bit better. So if you think about Q, right, note that, right, we have this area here, right? This is this area that we're going to integrate to find Q, right? So it has a centroid here. I've kind of drawn over it, and that's what's denoted here. So y prime bar is the location of the centroid of that area, all right? Now, you recall from statics that we can actually calculate that from the following integral. That's going to be the integral over this area. So that's the integral from y prime to c of y dA over the total area, which is the integral from y prime c dA. So this integral up here on the top, right, that is Q. That's exactly the Q we've defined up here that we need in our shear stress equation. And this integral down here is the area of the cross, the area where we're going to do integrate for Q. So that, according to this diagram, is A prime. So that means that actually to get Q, I can get Q, instead of doing the integral, it's simply the location of the centroid of that area A prime times the area A prime. And so that's very often a much simpler way to calculate Q. So for example, unless you have this shape that, this spam shaped crossbeam, most often you'd have something that's like maybe a rectangle, right? And you have a neutral axis here. And let's say you wanted to find Q at, you want to find this plane where this is like y prime. So this is my area A prime. It's pretty easy to figure out the value of y prime and then to directly calculate Q. So for example, if this is 1 inch and let's say this is 10 inches, and let's say you want to find this down at a height 2 inches from the top. So y prime here is actually 5 is actually 3 inches, right? To get Q for this, A prime is going to be the 1 inch times the 2 inches. So that's 2 inches squared. And then y bar prime, I should do this, y bar prime. That's going to be 1 inch down from the top. So that's 5 minus 1. That's equal to 4 inches. So in this particular case, Q would just be 8 inches cubed. All right. So that makes the calculation of Q a lot easier. You don't have to do the integral. You just have to do the, the area of the region you would integrate for Q multiplied by the location of its centroid. All right. So that's it. So remember, we want to get the shear stress on a particular plane. So that's going to define Y prime, right? The area above it, that's what we're going to use to calculate Q. The thickness at that plane is T. And then V and I are just the same things we used in chapter 6. Okay. All right. So let's do a quick problem here. All right. So let's find the null. Let's do problem 7-1. These are, let's first get this going. So maybe we'll do a couple of these. These are all kind of related. They're like the same problem, the same geometry, so they're not too hard to answer. All right, so you should see the whiteboard thing, I guess, now, right? So let's do problem 5-1. So here is an I-beam shown here, right? And they tell you the shear acting on that cross section, right? That would be from a shear diagram. And they want you to find the shear stress that you would see at point A. So if we were to kind of zoom in here, the plane that we're trying to find the shear stress on is this plane here, basically where the mid-web, that web meets the top flange, okay? So what's the shear acting on that area? All right. So this is symmetric, so we know that the neutral axis goes right through the middle. So like if I were to draw this cross section, right? We want to find, here's the neutral axis location. It's going to be, the total height is 340 millimeters, right? So this is, so the half height is 170 millimeters. Right, that's where the neutral axis is. And we want to find the shear stress acting at that point A. And so that is going to be at a distance here of 150 millimeters. So that is my Y prime. It's 150 millimeters. Okay. So we need the shear stress. So it's going to be tau equals VQ on IT. All right, so in this case, we know that V equals the 200 kilonewtons, I mean the 20 kilonewtons. Q we got to calculate. The Q is going to be the Q of this area, maybe. See that shaded area? That's going to be the area that we want to calculate Q. We need the Q of this for that area, right? That's the area above the plane where the point A is, right? So we can calculate Q. That's going to be A prime times Y bar prime, right? That's the area here. So in this particular case, the area that's shaded, A prime, is going to be 200 millimeters, times 20 millimeters squared, right? Or in other words, A prime is equal to 4,000 millimeters squared. Okay? I'm sorry, A prime. Now, Y bar prime, the distance from the neutral axis to the centroid, that's this distance here, that's going to equal 150 millimeters plus half of the height of the flange. So that's going to be 160 millimeters, right? And so that gives me a value of Q of just the 160 millimeters times the 4,000 millimeters squared, or in other words, that is that is 640,000 millimeters cubed, right? That is Q. Or, you know, if we want to convert it all to meters, that would be divided by 10 to the 9th, right? Which would be it would be 0.640 to the minus third meters cubed, right? So it's, you know, it's one or the other, right? Same difference. Okay, so we got Q, we've got V. Now, T is going to be the thickness of the cross section at A, okay? So that, you know, is this distance right here. That is T. It's going to be the 20 millimeters, right? You know, you might think, why isn't it this larger distance? But that's not really the thickness of the cross section that's carrying the load, right? That's this area here, right? And so that is T, and it's equal to 20 millimeters. All right. Okay. So now the last thing we have to do is calculate I, right? So I is the I for the entire cross section, right? For the whole thing, for the I beam. So to get the I for the I beam, I'm going to take the I for the full outer rectangular section, and then I'm going to subtract the I from these little cutouts. Does that make sense? Like this is the negative area, right? These little side cuts. And the reason I'm doing that is because I don't have to do parallel axis or anything, right? It makes my life a little easier. So this is going to equal 1/12 base times height of the full rectangular cross section. So there the base is 0.2 meters times the height, which is 340, right? 0.34 meters cubed over 12 minus, you know, the I of these guys here. So the base, I'm going to use this base plus this base, or you could do it for 1 and multiply it by 2. It doesn't really matter. So that base is going to be 200 minus 20, or 180 millimeters, 0.18 meters. And this height here is the 300 millimeters, or 0.3 meters. but that's going to be cubed, and that's all over 12. And so we can calculate that. Okay, and that gives me 0.250 to the minus third meters to the fourth. Okay. And so now I got everything. So now I can figure out the shear stress. Tau is V, which is the 20 kilonewtons, right? V times Q. Q we calculated here is 0.64 to the minus 3 meters cubed. VQ over I, we just calculated that here, 0.25 to the minus third meters to the fourth. And then times the thickness, and the thickness of that cross section, right, is 0.02 meters. And so upstairs I have a meters cubed, and downstairs I have meters to the fifth. So that means I'm going to be left with meters squared down in the denominator. So this is going to give me an answer in kilopascals, right? Because I got kilonewtons upstairs. And I get 22,560 kilopascals, or 2.56 megapascals. So that's the shear stress you would see on that plane A, okay? So it's pretty plug and chug, but you got to be careful about recognizing the plane that you're, want to find the shear stress at, because that's going to change Q as well as T, right? Those change Q and T depending upon what plane you're at. V and I are going to be the same for either one, okay? So you can't just look at a beam and say, okay, what's the transverse shear stress due to bending? You have to say, what's the transverse shear stress due to bending at this plane, a distance, 10 millimeters from the neutral axis or something like that, all right? Okay. All right. So now, same beam. Here's the question. Find the maximum shear stress. So they don't tell us the plane. So we have to figure out what plane are we going to find the maximum shear stress. So if tau, the shear stress, is equal to VQ on IT, and we know that V and I are constant, on the cross section. Where do you think you're going to find the maximum shear stress? At what plane? Oops. Where is the maximum shear stress going to occur?
Where like at the top and the bottom of the figure, like where the maximum normal stress is located.
Yeah, well, actually, think about it. So if you're saying, like, let's find, you're saying that the max shear stress should happen up at y prime equal to c, correct? at the top or the bottom, right? You're saying right up
Uh-huh.
here. Right? Okay. Now, what's the area we would use to calculate Q for that? If that's the case, at y prime equal to c, Q is actually going to go to 0. And that's because there is no area, you know what I mean, right? Above that plane. So actually, at the top and the bottom, it's the opposite situation. The shear stress is always going to go to 0 because the area is. So what do you want to have happen? You want to get the shear stress to be as big as possible. You want Q to be as big as possible, correct? And you want the thickness to be as small as possible. Where do you think you're going to get the maximum Q?
The closest to the neutral axis.
That's correct. Perfect. Yeah, excellent. The max Q is going to happen when you consider like that whole section, right? So this is going to happen. So Q is max. Right. Q is max when y prime equals 0. That's at the neutral axis, right? Yes. And now in this particular case, the thickness is also minimum there as well, right? So in this particular case, you would get the maximum shear stress right at the neutral axis, all right? In general, that is where you're going to get it. In general, if you were to kind of plot over the cross section, tau, now obviously tau is going to be like a shear acting on this face. Your maximum tau is going to be at the middle, and then it's going to go to 0 at the end. So it sort of has, it actually has like a parabolic distribution like that. Now, you could have some weird geometry like this, I think, right? You could have a geometry maybe like let's imagine we had a plus sign as our geometry, right? That's supposed to be a plus sign. So here, right through the middle, you would get the maximum Q, but actually T is pretty big here. So in this case, just above that is probably where you're going to have the biggest value of the shear stress. Because even though Q is max right at the neutral axis, we just go a little bit above the neutral axis and T changes to be quite a bit smaller than it would be at the neutral axis. Does that make sense? So in general, it is at the neutral axis is the max shear. At the neutral axis, you're going to get the max value for Q. So unless you have something weird, like a weird pear-shaped thing, right? Or something like that, you're going to get the maximum shear stress at the neutral axis. All right. So you could redo this problem and just figure out Q for this area here. And that's the only thing that would change. So in fact, to calculate that Q, oops. We could just break this up into 2 sections and just calculate the Q for each one of these sections, right? So here's our neutral axis. So if you wanted to get, I'm going to call this one section 1 and this section 2. So if you wanted to get Q for this problem, we're going to get Q for 1 and add on to it Q for 2, all right? Now Q for 1, here is y bar prime for 1, and that's going to be half of the, this distance here is 150, right? So that means y bar prime for section 1 is going to be 75 millimeters. And then the area prime for 1 is going to be 150 millimeters times the thickness, which is 20 millimeters, right? And so if we, which is 3,000 millimeters squared, right? And so for that one, I would get Q for the bottom shape is going to equal all right. And then for the top shape, actually, this is the same Q that I calculated in the first problem. So we already have that, right? That is, and there really isn't a need to do parallax on these because we're getting it, the Y bar primes from the neutral axis. So Q there was 640, right? So in this case, the Q total is going to be the 225 plus the 640. So you can see Q has gone up, T actually stayed the same. So the shear stress is going to be there. We can figure that out, right? So in this case, so V is the same. Q is now going to be I is still the same as we had before. I forget what that was. 2.25, right? And T is still the same, 20 millimeters, right? And that gives me 3.46 megapascals, right? So it's gone up, right? Okay. Now, what's the last one? What does the last one tell you? Oh, okay. It wants you to figure out the shear force resisted by the web of the beam. Okay. All right. So, when they talk, well, before I do that one, let me talk about shear flow. Although we can do this without shear flow, but yeah. Yeah, let me go back and go to my notes, okay, before we do this one. All right. So, all right, any questions on that before we talk a little bit about shear flow? So again, it's easy, but but students always have trouble getting these problems right. And the reason is that they don't spend the time just kind of trying to remember what all those letters in the equations, what they conceptually mean, okay? And that's really what you need to do, okay? So that's why I'm kind of being a little bit come on. All right. I don't know what that means. All right, so let's talk about another concept here. So let's talk about shear flow. This is actually a pretty important concept for dealing with these sorts of like I-beam types of shapes, not only to figure out what the stresses are in some of the regions, but very often we have these built up sections, like what's shown here is a section that might be built up by several pieces of wood. And so they're fabricated. I think in this picture, we can assume that they're glued together somehow, but they might also have nails going through those. And so you know, not only do we have to worry about whether the wood itself will fail, we have to worry about will the glue joint or the nail joint fail. And so shear flow is a concept that helps us design those sections as well. Okay. So the idea with shear flow, let's talk about, okay, let's not do that. Let's talk about this plane here. All right. Which we kind of did before. So if we look at this plane and we draw it out, we know that we have, I removed the top board, right? And so we have this is just what's left. And there's a neutral axis going through here, right? So we've removed the top board. This would be, let's say this is the glue joint, right? Well, there we go. Okay, that's the glue joint, all right? So we can figure out the force, the shear force acting on this glue joint, right? This shear force here, well, we'll call it delta V for now, right? Because this distance here, we'll do it over a finite section. Like just like they do in this. So this distance here is the delta X, okay? So we know the shear stress on here. We could calculate that. We can get that tau. That's going to be the VQ on IT, right? Okay, so we calculate that. Now, flow Q. I'm going to define that as this shear force per length. Okay. All right. So we'll talk about how you calculate it now, but like, let's say we could figure out the shear force, the shear flow Q acting on that glue joint. So it would be something like, okay, the shear flow on that glue joint is 2,000 pounds per inch. So that means every inch of distance down the length of that glue joint, you're going to see another 2,000 pounds of shear force that has to be picked up. So let's say the glue can hold, or let's say you're going to do fasteners, and fasteners can hold 2,000 pounds of force, shear force. Then that means you need to have a fastener spaced every inch to pick that up, okay? All right, I'll talk about the calculations in a second, but I'm trying to express conceptually what's going on here. So this idea of knowing the amount of shear force per length on a joint, the shear flow is useful. The other way we can define this, if you look at this, and we recognize that, so here's T, right? This is T, okay? So we know that tau is the shear force over the area. And in this case, that area is going to be the length, right? Let's call this the length, times the thickness, right? So that's this area here. And here you can see we have the shear flow Q. So we can also write the shear flow Q as the shear stress the VQ on IT stress, times the thickness. All right. And this is very often the way you see it. All right. The other thing you can do is if you recognize that tau is VQ on IT and you put that into here, the T's will cancel out and you also get that the shear flow is VQ on I. All right. So those are the most common ways that we calculate the shear flow. Now, the nice thing about the shear flow is Q is going to give you the shear force. Well, I'll write it once.
Sir, are you writing right now on the screen?
Yeah.
Yeah, because it got frozen like from when you wrote shear flow, the top equation.
Oh, really?
Yeah, we are not seeing any of the other stuff you wrote.
Let's try. But you can see the slide?
Yeah, but it's kind of like, I don't know, like pixelate. It's not the same quality.
Zoom is not responding, it says. What's going on here? Okay, don't go away. I might leave the meeting and come back in. What is going on? All right, I'm back. Let's see if I can try this again. All right. Do you see the marked up PowerPoint slide now?
Yes, sir.
And you can see all the,
Yeah,
you can see it now? Okay, I have no idea what that was. All right. Sorry about that. Can you see it now? Still?
yes, sir. Yeah, it's good now.
Thanks. All right. So conceptually, this shear flow is the shear force per length of the joint. And we could calculate it in either of these two equations, all right? Either VQ on I or the shear stress times the thickness, okay? Actually, this is probably the most useful way to calculate it in this chapter, all right? It's basically, if the shear stress is VQ on IT, you multiply it by T, you just get VQ on I. All right, but what does this mean? So this allows me to design the joint. So you can use this to design the joint. So for example, let's say we figure out Q is 1,000 pounds per inch. Okay, that's our shear flow, 1,000 pounds per inch. And let's say a nail has an allowable force, shear force, of 500 pounds. What's the nail spacing that you need to have on that line? How many nails, or how many nails per inch do you need, or like, what's the spacing between the nails? The shear flow on the joint, like let's say we're going to put nails in here, right? Nail, 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 right? The shear flow on that joint is 1,000 pounds per every inch along the beam length. And each nail can take 500 pounds of shear. What is going to be my nail spacing? S.
Can't we just put a nail every half inch?
That's right. That's right. A nail every half inch. Right. You have to do a nail every half inch. Right. Right. That's right. So how do you get that? The spacing is going to be the allowable force over the shear flow. Okay? That's it. All right. Now, you could do the same thing with a glue joint, but it doesn't really have spacing. You know what I mean? Right. But you could also figure out what's the max, whether a glue joint will fail or a weld will fail as well. Right. But if we're going to use fasteners, nails, rivets, bolts, whatever, shear flow helps us easily design like how many rivets we need on the rivet line or whatnot. Okay. All right. So the spacing is going to be the allowable shear stress in the fastener divided by the shear flow, right? Because the shear flow gives us how much shear force per unit length on that joint. Okay. All right. All right. Do I have another slide? I do not. Oh, there's my fastener spacing slide. Okay, but let's take this one more step. Let's do the same problem. Let's step back a little bit. Maybe. It doesn't erase so well on this thing. I don't know. Where's it? Erase that. What's this thing doing? Okay, let's just discard all this. All right, so that's how we can do the nail joint to nail the top board onto the middle web, right? What about these sideboards? Let me erase all this stuff. Let's give me a little more room. All right, so let's say we've got these sideboards and I'm going to nail these in also from the side, okay? How could we calculate the nail spacing from the sides, right? Again, we have some given allowable shear force for the nail. Still, we're going to use that the spacing is the allowable over the shear flow, right? Q. But how would we get Q on this section? So we need to get Q on this plane here. Oops. All right. So obviously we have to calculate lowercase q, the shear flow, right? And so let's assume that V is given, right? And all the geometry is given. You can calculate I for the whole shape. That's easy. We know how to do that. So my question is, what is the area that we should use to calculate Q if we want to get the shear flow on this surface?
It wouldn't be like the plane where the shear will act for that certain part.
Okay, so, but now look, like if we zoom in, right, I'm going to draw it really. So there it is, right? There's the nail joint, right? So what plane do you want to use? Where do
Like
you want
the only part, like not the whole plane, just like the top section, you know?
Yeah. Okay. So like we don't like this plane doesn't really make sense, right? Because that's, you know, I mean, that's not where the nail line is, right? You want to use this section, this plane? Is that what you're saying?
Yes, sir.
All right. But what would we use? What is y prime and what's a prime for that? Or y bar prime and a prime? Like remember before what we were doing, like in this particular case, right? We're going to use the Q of this entire area to calculate if we wanted to get the shear flow through that shape, we use the Q of this all upper T. So what should be the area that we use for calculating the Q on the side joints? Okay, it's a little tricky, but the answer is kind of here with this picture. And the actual area you're supposed to use, I'll just say it. If we're going to do this, here's the sideboard, right? And here's the nail joint, right? Going in here, right? Here are the nails, right? The area we're actually going to use is this whole region, okay? So this is actually going to be the area we use to calculate Q. Right? So we can figure out a prime from this, and then we can figure out the distance from its centroid down to the neutral axis. That's going to be the y bar prime. Okay, y prime bar, what are we going to call it, right? Now, the reason why we use that is, again, you have to go back to kind of the derivation, right? So you have this whole section here is, remember when we drew the picture to get the shear formula, right? We had a region with axial force due to bending on one side, and on the other, it was a little greater on this side. We had an F plus a delta F, and on this side, we just had F, right? And when we did this, we said, okay, the shear stress here has to be such that it picks up the delta F. Well, it's still the same concept, but unfortunately, this shear stress, there's nothing down here to pick it up. That actually gets transmitted through this region here. So it would be the same shear stress you would expect to see if there was material down here, which there isn't, but it still has to balance the same amount. So instead of being applied down here on this bottom surface, it actually gets applied through the nail line. And if you think of it that way, then it's obvious why we should use this area, okay? Does that make sense? I know that's a little bit, it seems a little bit odd, but if you think about it that way, I think it makes a little bit more sense, okay? Sometimes people are like, well, let's pick the middle area here, like this shear plane, but that's not actually correct. We want to use this area because the shear force that comes about from this differential area here, that is what gets transmitted through this joint, okay? That shear plane. And that's actually that's what they're trying to show here in this figure, right? Here's the force due to bending on the left side of that little segment. Here's the force due to bending on the right side, plus the little bit extra. And that little bit extra, instead of being picked up on the bottom where there's no material, actually gets picked up through the nail joint, okay? So same calculation, you just have to pick the correct area to calculate Q. Once you get that, you can calculate the shear flow, lowercase q, and then it's the same, as the argument we used to calculate the nail spacing on that one. Does that make sense? All right, let's do an example, okay? Let's do an example. Let's find a good example. Let's do this one. 733. Okay. So we'll do 733. All right, hold a second. Now I'm gonna share the screen, so let me know if you don't see it. All right, so now you should see the grid paper with the problem set. What? Oh, but that's the wrong problem. I don't want to do that problem. Okay, but you see the grid paper, right? Let me get the right problem. I thought I copied that. It's blank, I know. All right, so now you see the grid paper and you should see the problem statement, correct? Okay, I'm going to assume that that's a yes. I don't say anything. All right, so here we have two boards, same size boards, and they're nailed together with this nail pattern here, right? So there's 3 nails on a line, and each line is spaced out 4 inches. Here it wants you to find out the shear force that has to get picked up by each nail. So we want to find the shear force in each nail. Okay, well, let's first figure out the shear flow. That's going to be lowercase q. That's the shear force over capital Q over I, right? Now, the plane we're interested in is going to be right here at the middle where the 2 boards are nailed together. That's actually also the neutral axis of the beam. So the shear force there will be maximal, okay? Or the shear stress there will be maximal. All right. So to compute uppercase Q, we're going to use this area. All right. So V we know, right? V is equal to 900 pounds, right? we need to calculate Q and I. So this is the area, like I said before, we're going to use to calculate Q. Here's the middle. So we're going to use this area here to calculate Q. All right. So this is Y bar prime, and that's half the board height. So that's 1.5 inches. And the area here, A prime, is the cross-sectional area of one of these boards. So that's 3 inches times the 9 inches, or 27 inches squared, right? So the Q we would use there is A prime times Y bar prime, or 1.5 times 27. So that's 40.5 inches cubed. Now the I is going to be the I of the entire cross section, right? We want the I of the entire cross section. And so that I is 1/12 the base times the height. The base is 9 inches, and then the height is 6 inches, correct? 6 inches cubed over 12. And so that gives me an I equal to 162 inches to the 4th. All right. So now we can get the shear flow lowercase q. That is the 900 pounds, right? Times uppercase Q, the area Q, that's the 40.5 inches cubed over I. So I is 162 inches to the 4th. So you see, I'm going to be left here with units of pounds per inch, right? Shear force per length. And I get a shear force, a shear flow, excuse me, of 225 pounds per inch. Okay. All right. So that's how much shear acts per length on this joint. All right. Now, how would we figure out the force, the shear force in each nail? How could we get that?
I don't know. Divide them by the number of nails, probably.
Do we multiply by the 4 inches? Or no?
Well, try to think about it. Instead of just kind of guessing like with what numbers are shown in the picture, think about, okay, so we know how much force per length, right? So, right? So how much force is picked up by one of these patterns of 3 nails? How much shear force is picked up by those 3 nails that I just highlighted there?
Would you use the spacing equation?
How so?
Since S equals the force allowed over Q, you would just
Oh, okay,
rearrange
right.
it.
So we had right. You know, you could do that. This would give you the force would equal S times Q, right? Where this is basically S, right? The 4 inches. Okay, so let's do that. We can calculate that, right? So 4 inches times Q, which is 225 pounds per inch. That is going to give me a value of just pounds, correct? So that's 900 pounds. So on this area here, there is 900 pounds of shear force. Okay. But how much is picked up by one nail? Right, this 900 is actually picked up by three nails, right? Does that make sense? Every 4 inches, right? There's going to be 900 pounds of shear force. The way this beam is designed, we put 3 nails. You know, it's not just one nail, it's 3 nails in parallel going down the spacing, right? So those 3 nails pick up the 900 pounds of force. So that means each nail is going to be 900 divided by 3. So each nail is 300 pounds. Okay. This is a classic example of what I kind of keep bringing up from the beginning of the semester, right? When you see equations or when you see problems worked out, you can't just sort of blindly plug numbers into letters as they might have been done in other problems. Each equation is actually like a concept. So you have to understand conceptually, you know, what we're talking about, what's geometrically, what's the picture conveyed by each one of these equations. So like in this particular case, to be able to recognize that whole thing about the shear flow, Q being the shear force per length, okay? So it's per length of that beam, right? And so that's what, if you understand that, then it's obvious that we have to divide each nail, you know, that this length here of 4 inches is actually picked up by the 3 nails, okay? If it's one nail, it would see all 900 pounds, right? Okay. And that's pretty much it for this chapter. That's what it is. So like I said, you understand how to calculate the shear stress, the transverse shear stress due to bending on a particular plane. So you have to know, okay, what's the cross-sectional area that I'm going to use to calculate Q? You know, what's the plane of interest? And then the area above that is the area used to calculate Q. All right. So, and also you get the T from that. So point 1. Okay. Now the second point is when we deal with these sort of built up sections, right? With the nail lines or the rivet lines or whatever. Shear flow is a good way to do it. You actually don't need to use shear flow. You could have figured out tau on this surface and then said, okay, each nail sees a certain area like that. But, you know, I think shear flow is easier way to think about it, right? But you have to understand the concept that it's the shear down the joint, you know, per unit length, okay? And so that could either allow you to figure out what's the shear force seen in each fastener, or you could figure out the spacing of the fasteners, okay? Given like an allowable stress, okay? Or allowable force, I should say. All right, so again, not too hard, but you have to kind of try to spend a little bit of time really understanding the concepts and not just sort of blindly following the steps taken in some example problems, okay? All right. Any questions on that before I stop class? Because I think we're at the end here anyway. All right. Have a good weekend.